Hello students, this is Professor V.N. Mawar. I am going to introduce a solvent extraction which is important mass transfer operation in chemical process industry to separate the liquid mixtures. Solvent extraction is also known as a liquid-liquid extraction. It's the separation of the constituents of a liquid solution based on their relative solubilities into different immiscible solvent. Usually they are water and other organic liquids. The liquid solution which is to be extracted is termed as feed solution, which is a mixture of solute and a carrier liquid as a solvent is brought into intimate contact with other immiscible or partially miscible extracting solvent in order to achieve the transfer of the solute from feed solution to extracting solvent. If the substances constituting the original solution distribute themselves differently between the two liquid phases, a certain degree of separation can be achieved. And these two phases separated, one of them is called as solvent-rich phase, is termed as an extract phase, whereas solute-lean phase or residual phase from which the solute is to be extracted is the raffinate phase. This figure indicates that the feed solution is brought into contact with the solvent in the first contacting phase, which is followed by the settling phenomena to separate the two different phases as an extract phase and the raffinate phase. Here we will study this mechanism of the solvent extraction in the different steps. First of all, this figure indicates the one mixer provided so as to make intimate contact between the feed solution and the extracting solvent using the contacting device called as a mixer. And the second, which is followed by the second stage for the settling to achieve the separation of extract and the raffinate phase based on their difference in the densities. Then further, after the extract phase and the raffinate phase is achieved, then the removal and the recovery of the solute from the extract phase in a relatively pure form can be done. Further, the recovery of the solvent from each phase can also be done by the separation processes such as the distillation. So here we have some importance of extraction over the distillation for particular operations. Here we will be studying why the extraction is important over the distillation. In some cases, such as whenever the components to be separated have close boiling points and if their relative volatility is close to unity, then separation becomes difficult by distillation. So the extraction is favored. In the second case, where the separation of the heat sensitive materials to be carried out, such as antibiotics, vitamins, particularly pharmaceutical products, then we have to follow the extraction operation. Then third is the recovery of non-volatile solute, usually from aqueous solution in hydrometallurgy, where the latent heat of water is very high, and this can be achieved by extraction rather than distillation. Whenever the large amount of latent heats are involved in the recovery of the solute from more dilute solution using the distillation operation, then in that case the extraction is always favored. The removal of organics from aqueous solutions such as phenols from aqueous waste, then we should prefer extraction operation. Extraction offers more flexibility in the choice of operating conditions as well over the distillation. In a typical solvent extraction operation, only about 5% capital cost and 15% operating cost is involved for the extractor, whereas 85% capital cost and 95% of the operating cost is required for the equipments of the solvent recovery and the product purification. If you compare it, the extraction requires a very low cost followed by the separation, which is the highest cost, but the extraction cannot stand alone without separation. And that's why whenever it is possible to carry out the separation by the distillation and other phenomena, we generally prefer these operations. But in some cases, if the extraction is having no choice, then we should go for the extraction. So we have some examples such as the separation of acetic acid from dilute aqueous solution. Then second is a long chain fatty acids can be removed from vegetable oils by extraction with liquid propane. A separation of the close boiling isomers, particularly in petroleum products. For example, separation of the different aromatics from lube oil by using furfural as a solvent. Recovery of the penicillin from the fermentation broth using amyl acetate or butyl acetate or MIBK can be done using extraction operation. Then selection criteria of solvent as an extracting solvent for extraction operation. The choice of the solvent is influenced by the factors such as the high selectivity, also called as a selection factor, the ratio of the concentration ratio of the solute to feed solvent in the extract phase to that in the raffinate phase is called as the selectivity or the selection factor. The measure of ability or the effectiveness of a solvent is measured to extract a component or a class of the component in preference to others. This factor will determine the number of extraction stages required. The selectivity should be greater than 1 to achieve the separation. If the selectivity is unity, no separation is possible. The higher selectivity is always desirable to carry out the extraction operation for the ease of separation, consuming the lesser solvent. Second criteria is the distribution or the partition coefficient, which is also important. It is a ratio of the concentration of the solute in two phases. It is indicated by K, is written in the form of equation, is the ratio of the concentrations of the in extract phase to the concentration in the raffinate phase. Higher values of the distribution coefficients are generally desirable for less amount of the solvent and less number of stages required for the desired separation. Third criteria for this solvent is the recoverability. The solvent should not form an azeotrope with the extracted solute. The higher relative volatility of extract mixture or extract phase is always favorable for easy recoverability of the solvent. Then fourth is the density. The greater the density difference between the feed and the solvent, the easier is the separation. Interfacial tension is one of the selection criteria, should be high for the coalescence of emulsions to occur more readily. Then chemical reactivity, the solvent should be non-reactive because we have the physical separation only. Insolubility of the solvent should be insoluble with the feed solvent. Then the properties such as the viscosity, vapor pressure and freezing point, the value should be low. Low viscosity is always favorable for the easy separation, and the low vapor pressure is always desirable. The solvent, extracting solvent, should be non-toxic, non-flammable, as well as it is of low cost. It is cheaply available. Then the important point when we'll discuss on the solvent extraction is liquid-liquid equilibrium. Whenever any mass transfer operation is to be studied, then the equilibrium characteristics must be learned. So in particularly for this liquid-liquid equilibria, in the liquid-liquid extraction system contains at least three components. First is the feed solution contains the solute C and the carrier liquid as a feed solvent A. Which is the feed solution is contact with the extracting solvent B for extraction. So that's why the three components are involved. We also call as the liquid-liquid system, liquid-liquid extraction system as a ternary system. And in this ternary system, the three binary systems can be formed such as A with B, B with C or C with A. There depends upon the mutual solubility. The mutual solubility behavior of the component determine the nature of the equilibrium characteristics. So there are the two types of the systems, ternary systems, which is present in the liquid-liquid extraction operations. First is the carrier solvent A and the extracting solvent B are practically immiscible, and the solute C is miscible with carrier solvent A and the extracting solvent B in all proportions. So the solute C will be distributed between the extract phase and the raffinate phase in different proportion based on its solubility in these two different solvents. Second type, the solute C is completely or partially miscible with the carrier solvent. It is completely miscible with carrier solvent, but both solute C and the carrier solvent have limited miscibility with the extracting solvent B. That means the type 2 consists of solute C is means both the solvents are partially miscible with each other. So here we can find the different type of the mixtures, binary mixtures in this case. So we'll be studying one by one. Now here, first of all, whenever we want to study the equilibrium characteristics of extraction, liquid-liquid extraction operation, so we have to study the equilateral triangular coordinates or equilateral triangular diagram to discuss the equilibrium characteristics. If the feed solution F contains the solute C and the feed solvent A, which is contacted with the extracting solvent B for the extraction, leads to solvent-rich phase as extract phase E and the solute-lean phase as a raffinate phase in the form of R. So this equilateral triangular diagram, here we will be studying the two different cases. First of all, the apex of the equilateral triangle indicates the 100% of each component. Say A here 100%, C solute is 100% at the top, and another extracting solvent B showing the 100%. Here, if we want to study the percentage, their percentage goes on decreasing. Percentage of A goes on decreasing as moved towards the C. The sides of the equilateral triangle indicates the percentage of A and C only. B is absent on these sides, each side. Each side of the equilateral triangle indicates only the composition of the two components. Here this AB shows only the proportions of A and B, and whereas the AC side AC indicates only the proportion concentration of A and the C in the different proportions. If we see the concentration at the apex A is showing the 100% of A, where it is decreased subsequently with up to the point C, where it is 0 at point C, where the solute C is 100%. Whereas the solute C is again going to decrease in the downward direction. Similarly, we have the percentage B on the percentage B is 100% at apex B, but it is decreased in the direction towards A. Now here if you see the point M, what is the concentration or the composition of M, point M? The perpendicular distance between the point and the side indicate the concentration of C, side AB. If you see the composition, the perpendicular distance indicates the percentage of C. That is here we have the 60% of C indicates this one, perpendicular C. Whereas the perpendicular distance at this point indicates the percentage of A, if it is shown here also. So here is the composition of M indicate 20% of A. So if you see that 100% goes on decreasing like this, here if you want to determine the concentration at any point in the equilateral triangle, uh, here first of all we'll see that there are the two approaches. First is the case one. Here I will show you the sides indicates the percentage of A and the C components, whereas every side indicates the only two components. The third component is absent. First of all, if you see the concentration at point M, it shows that 20% of A carrier liquids. If you line this, this is 100%, and if you see this line gives you 80% of A, 60% of A, then it goes on decreasing. This line indicates the decrease in the percentage of A. So this point lies on the 20% of A line. So here we have the 20% A. Whereas if you see the 100% B, here is the B is the 100% composition, and if this line, this inclined lines, the indicates the this 80% of AB, then 60% of B. Similarly, it goes on decreasing this 40% of B, whereas this 20% of B, where the point M also lies on the 20% of B. That's why we called it as 20% of B. And the solute C is 60%. If you see that here 100%, here 100% C, where and this kind 80% of C on this line, then 60% on this line. So point M also lies on the 60% of C. That's why we can determine the solute concentration C as a 60% at point M. Another approach showing the perpendicular distance. Here in the case 2, if I see the percentage, it is understood that the percentage of composition of the concentration or the composition at point M is indicated for this percentage C is the perpendicular distance between the point and the line in front of the point. This is this line. This indicates perpendicular distance between the line and the point is giving you the percentage of C. Whereas this percentage here, it is shown as a 60% solute, 60% C. Whereas the perpendicular distance from the point M on the side AC gives you the percentage of B. This is indicated that 24%. Okay. Whereas the perpendicular distance between the point M and the side BC gives you the percentage of A. That is, here it is shown that percentage of here it is only 16% of the A in front of this, and every sides of the equilateral triangle gives you the composition of only two components. Here that this AC indicates the composition of AC, whereas composition A and C, whereas the AB indicates the composition of A and B only, whereas the composition of B on the side BC gives you the concentration of B and the C only, where the A is absent. Now here first of all we'll see the first case, that is solute C is miscible with A and B, which is shown by the equilateral triangular diagram. Here we have the curve. RPS is an equilibrium diagram within the equilateral triangle. If you plot the equilibrium characteristics, equilibrium concentrations on the point, which is we obtain as a binodal, called as a binodal solubility curve. Binodal solubility curve is nothing but the two curves or the two arms, say RP, indicating the concentration of the raffinate phase, whereas the curve PS indicate the concentration of the extract phase which are in equilibrium. The concentration at any point above this curve showing the homogeneous phase or the single phase region. It is a single phase region above this curve, binodal solubility curve, whereas the concentration at any point, concentration of the mixture at any point beneath this curve gives you two phase region or this mixture of the two phases. Suppose we have now here the G1 and H1 are the two phases in equilibrium. G1 and H1 are two phases in equilibrium where the line joining the two equilibrium characteristics or the two equilibrium concentration is called as a tie line, whereas the curve for the raffinate phase and the curve for the extract phase merge at a point called as a plate point. The point P is indicated as a plate point. A liquid mixture having the overall composition corresponding to point K is a two-phase mixtures. On equilibrium, it separates. This point 2 is when the feed solution is brought into contact and they mix up properly with the extracting solvent. A mixture will be formed at a point K and which is further separated, which is further settled down for the separation into two phases having the composition of the raffinate phase at point G2 and the composition of the extract phase at H2. They both, the composition of the point at the point G2 and H2 are in equilibrium, and this can be so concentrations can be determined or the composition can be determined by the mixture rule. If you take the ratios of G2, G2 divided by H2, that is the quantity of this raffinate phase and extract phase is nothing but the length of the KH2 divided by length of Kg2. Then again we have along with the equilateral triangular diagram, these equilibrium characteristics can be presented by the right angle triangular diagram. So the mass fraction of the solute in two phases as raffinate and extract phase at equilibrium are plotted against the corresponding mass fraction of the extracting solvent. The concentration of the extract phase are denoted by Y, YB and YC, and those of the raffinate phase are indicated by XA, XB and XC. The raffinate phase, yes, this is the right angle triangle in which the binodal solubility curve is plotted. The first arm PQ is showing for the raffinate phase, indicate the concentration of XB and XC, where the curve, solubility curve for the extract phase is indicated by the PR, and this is traced so as to get the coordinates in the form of YC and XC in this. So this is a diagonal and this is the curve showing the equilibrium curve for this liquid extraction. Now here the P is the plate point where the raffinate curve for the raffinate phase merge with the curve for the extract phase at a point P. The point D1 on the raffinate phase and the point D2 on the extract arm represent the composition at equilibrium, and they are connected by a tie line, that is they are connected by a line called as a tie line. So D1 and D2 is the tie line for this equilibrium concentration, and which is plotted here. See, here is the composition at equilibrium. The equilibrium diagram can also be drawn on XY coordinates. Now here the understanding of effect of temperature on the liquid-liquid extraction operation is also important. So the effect of temperature on extraction operation can be shown with the three-dimensional figure where the temperature is plotted vertically and the isothermal triangles are seen to be sections of the prism as shown in the figure. The This is the prism where the this is your isothermal section of the prism is indicated for this equilateral triangular diagram, where it is shown is a two-dimensional diagram. The mutual solubility of the feed solvent and the extracting solvent increases with increase in the temperature of the mixture in the extraction operation, and that's why if we have say the temperature T1, this binodal solubility curve looks like this. But if we increase the temperature from T1 to T2 and T2 to T3, subsequently the binodal solubility curve get reduced, and the homogeneous mixture, the solution where area of the homogeneous phase will be increased. The solubility, mutual solubility between the solvents increases. The increase of solubility at higher temperature influences this Ternary equilibrium considerably. The critical solution temperature, say this is the T4 is the critical solution temperature at which the phases dissolve completely to form the homogeneous single phase, which is not desirable. So here subsequently, if I increase the temperature from T1 to T2, T2 to T3 and T2 to T4, here we'll get the complete homogeneous solution. Here we do not get the binodal solubility curve, but a point called as a plate point. Here we'll have the homogeneous solution. So not only does the area of the heterogeneity decrease at higher temperature, but the slopes of the tie lines also get changed with the change of the effect of temperature. Now here we see the methods of operations for the solvent extraction. So we have the stage-wise contact and the differential continuous contact. So these are classified. The operations of solvent extractions are classified based on their type of the contact. First is stage-wise contact, and the second is a differential continuous contact. So stage-wise contact is classified as a single stage operation and multi-stage operation. Multi-stage operation is further classified as a cross current, counter current and co-current. Whereas the differential continuous contact having some equipments such as the pack columns, spray columns, pulse columns and rotating disc contactors. Now here we have the single stage operation. So we'll consider the single stage operations. Under the single stage operation, we'll be studying the two different cases. In the first case, we have the ternary system with immiscible solvents. The carrier solvent A and the extracting solvent B are practically immiscible. So here we have the solute C is miscible. Solute C present in the feed is completely miscible with the carrier solvent A to form the homogeneous feed solution, which is contacted with the extracting solvent, so that here the stage indicates both the mixing and the settling operation as a single stage 1. Then all the A in the feed solution after the settling will remain in the raffinate phase only. There is no change of the concentration of A in the raffinate phase, whereas all the B present in the solvent will remain in the extract phase after the separation. If you see, there is no need to use the triangular diagram in this case, particularly if F is the mass of the if F is the mass or the mass per unit time of the feed solution containing A kg and the C kg is contacted with the solvent B, followed by the settling in the single stage 1, the phases are removed in equilibrium as a raffinate phase and extract phase. If we have the nomenclature, say in the form of mass, the concentrations in the form of mass ratio, we have except that is a mass of C per mass of A in the feed solution. This is we define as the solvent free basis. So here we have the mass ratios, mass of C per mass of A in feed solution. Subsequently, we have X1 is the mass of C per mass of A in the raffinate concentration, whereas the Y1 for the extract phase and YS for the extracting solvent concentration initially present in the extracting solvent, that is YS. If it is pure solvent is used, YS is equal to 0. At an equilibrium, the raffinate and extractive phases are in equilibrium with the stages with the leaving concentration X1 and Y1. In the single stage operations, when the feed solution is contacted with the solvent so as to obtain the raffinate phase R1 and extract phase E1, where the feed solution contain only A. In this particularly case, where the ternary system with immiscible solvents, where the solvent A is perfectly immiscible with B, so as to give the raffinate R1 consists total amount of A, where the extract also consists of total amount of B mass of solvent, where the compositions of the solute are expressed in the different forms like this, where if you make the material balance of the components solute C is written, that is input is equal to output. Input means in terms of the feed solution, concentration of the solute in the feed solution is written as XF into A, plus the concentration of the solute C in the solvent in the form of B into YS is equal to the concentration of the solute C in the raffinate place plus concentration of the solute C in the extract phase. If you write here, we will get the particular form of equations. Here in the form of y1 minus ys upon x1 minus xf, it gives you minus a upon b. If you plot the line on the graph xy coordinate, here there is no need to use the equilateral triangular diagram to show the equilibrium characteristics, but only using the xy coordinate we can also plot the equilibrium characteristics for the system in which the feed solvent and extracting solvents are completely immiscible. So these equations shows the operating line for the single stage operation for the extraction, where if you see these indicate the lines indicate the line connecting the x1 and ys with the line connecting x1 and xf and y1 with x1 and xf this is with x1 and y1 here gives you a straight line having the slope minus AB, where we can determine how much the quantity of B to be determined and how much the concentration of the solute C in the extract as well as in the raffinate phase can be determined. In most of the cases, if the extracting solvent is pure, that is it is free from the solute initially, then we can take ys is equal to 0, then the operating line starts from the x-axis, where in this x and y coordinate, this extract composition is plotted against these raffinate compositions. In this case, the feed point, here is the feed point, here ys is equal to 0 can be taken at the point at the zero value of ys. So if ys is having certain value, the operating line will start from the particular point. But here if the extracting solvent is pure and it is free from the solute, y is taken is 0 and we should start this f point, that is operating line, from this 0 point, that is y1 minus xf and y1 upon x1 minus xf is equal to minus a upon b, gives you the amount of the solvent required for this particular operation as well as the composition of the extract and the raffinate phase can be determined with this. Now the second case for the single stage operation is this ternary system with one pair is partially miscible, where the carrier solvent as a feed solvent is partly miscible with the extracting solvent. The solute C is perfectly miscible with carrier solvent, whereas the carrier solvent and extracting solvent are partly miscible. Feed solution is contacted with mass S1. Now the solvent is indicated by S1 with now the concentration of the solute C for each system, for each feed as well as solvent and extract and raffinate are indicated by the weight fraction. Here the feed solution feed solution F is contacted with the solvent S1. Then the solvent containing the principally B with the Ys weight fraction of C, that is Ys into B is equal to S1. That if the solvent is pure, Ys is equal to 0, then S1 become equal to B, as seen in earlier case. After contacting and phase separation at equilibrium, raffinate R1 with the solute concentration X1 in the weight fraction of C and extract E1 with Y1 as a weight fraction of C. Here as indicated in the diagram, where the X1 and Y1 represent the equilibrium concentrations. Adding the solvent S to the feed solution F produces a mixture of M1, which on settling splits into the two equilibrium phases as E1 and R1. So first of all, the feed solution is mixed with the extracting solvent S to form a mixture that is indicated by M1, which is further separated so as to give the two different phases at equilibrium as E1 and R1. So overall material balance can be written as the feed solution is added with the solvent S1. S1 indicates the solvent fed to the stage 1. If this is a single stage operation, so we write here S1 is equal to M1, and that this is the mixture before settling, and this is the mixture after settling, that is in the form of two different phases. The M1 mixture is settled down into two phases, that is E1 and R1. If we plot a triangular diagram, so triangular diagram is required to indicate the equilibrium characteristics. So points E1 and R1 are connected by a tie line. So E1 and R1. So here the binodal solubility curve is plotted with the equilibrium characteristics for the given system. Now this point M1 lies on the line R1 as well as E1. Now the second line, this starts from the feed point. Feed point consists of only the component of A and C, which passes through the mixtures of and this S1, because this feed or the input is given in terms of addition of F and S to give rise to R1 and E1. So this M1 will lie on the line Fs as well as R1 and E1. E1 and R1 is a tie line. So if we can find out the composition of at point M, we can locate the composition of point M1 by using the mixture rule, as F upon S1 is equal to length of M1 S1 and F1 M1, like this. So one can locate the point M1 by computing the concentration of C in the mixtures M1. So we can also determine the value of XM1, the composition, and we can also locate according by making the solute material balance. If XM1 is the weight fraction of C in the mixture, then we write the solute material balance, and further we find this XM1 is equal to Fx1 plus S1 Y1 into this equation, and overall solute material balance yield, making the solute balance over the operations before settling, after mixing to form the mixtures, and mixture is settled down in the form of extract and the raffinate phase, where now here we'll obtain the value of extract phase, the quantity of extract phase obtained after the operations. So if you see these equilibrium characteristics can be also plotted on XY coordinate. The same diagram is written with this binodal solubility curve will be here, where these are the different tie lines, where the next point M1, that point M1 must lie in the heterogeneous area beneath the binodal solubility curve. The minimum amount of the solvent required is found by locating M1 at a point D, which provides an infinitesimal amount of extract at G. Extract G, higher amount of extract G will be obtained. The maximum amount of solvent required is found out by locating M1 at K, which provides the infinitesimal amount of raffinate at point 1. This point L, this is indicated by this understanding of this triangular diagram for the single stage operations. when the solvents such as feed solvent and extracting solvents are partly miscible with each other. Thank you.